Okay, let's unpack this. Imagine not just watching the brain's electrical symphony, but actually getting your hands on the controls,
Right.
understanding how it all works,
Hmm.
even teaching AI to spot really crucial patterns like seizures,
Mm-hmm.
and maybe even exploring the brain itself in 3D. Well,
Exactly.
that's what we're doing today. We're diving deep into EEG, electroencephalography.
Yeah.
We'll look at how synthetic fake signals help us understand
Yeah,
things
how we can model it.
and how AI is learning to spot neurological events, plus some really incredible visualization tools. We've
Yeah.
got info from an EEG simulator, some broader data tools, and
Mm-hmm.
specific AI projects on seizures.
And what's really striking here, I think, is just how powerful EEG is, even though it's not invasive. No surgery needed.
Right.
It gives us these amazing real-time glimpses into cognitive states, neurological problems, and this deep dive, it's really going to show you how we're demystifying these super complex signals, making it all more accessible.
Yeah, breaking it down. And, well, a big part of that starts with the basics, right? Like
Mm.
this advanced EEG signal simulator.
Yeah.
Let's talk about synthetic EEG signals.
Okay.
So these aren't just random squiggles. They're like carefully crafted waveforms made to act just like real brain activity.
Precisely engineered.
And the cool thing isn't just seeing the signals, it's how the simulator lets you sort of deconstruct and control what often looks like chaos in real brain activity.
Okay.
You're not just observing, say, alpha waves, you're understanding the actual mechanics behind them, how they get distorted things that are almost impossible to, isolate cleanly in real data.
That's exactly right. And for anyone who really wants to get a handle on EEG, this kind of simulator is, well, it's an amazing learning tool.
Yeah, for education.
Definitely.
Yeah.
You get this intuitive feel for how different brain states or those noisy artifacts show up in the raw signal that's the time domain view.
Okay.
And crucially, how that translates into the frequency view, the power spectrum. But it's also gold for engineers, for data scientists developing algorithms.
How so?
Well, they can test things like artifact removal or feature extraction using a signal where they know the ground truth. You just don't get that clean baseline with messy real-world recordings. It simplifies things, helps you build that intuition for how the different pieces add up.
So when you're playing around with a simulator like this, what's something like surprising or maybe counterintuitive that jumps out at you? Something you wouldn't just get from reading about EEG.
Good question. Well, the layout itself is pretty smart. You've got your controls on one side, your visualizations updating live on the other.
Right.
And under controls, you have these brain state presets. They're super handy. You click, say, relaxed meditative.
And boom, alpha waves pop up.
Exactly. You see that strong alpha presence, classic sign. But, real EEG is almost never that clean. It gets messy.
Artifacts, you mean?
Yeah, artifacts. The simulator lets you dial in two common ones. There's muscle artifacts,
Right.
EMG, that high-frequency noise you get from, like, clenching your jaw. And then eye blink artifacts, EOG. Those look like big, slow-wave spikes in the signal. Simulating these is so important because real data is full of this stuff. Learning to spot it and eventually filter it out is absolutely critical for accurate analysis.
Okay, so you've got the presets, the artifacts. What about digging deeper? Can you control the individual brainwaves themselves?
Oh, yeah, you get quite a bit of control. There are sliders to fine-tune waves, adjust the power, the amplitude of delta, theta, alpha, beta.
Okay.
And if you want to get really specific, there's an advanced mode. You can set the exact sender frequency, the bandwidth, the amplitude for each wave type individually.
And the visuals, what are we actually looking at?
Two main graphs. First is the simulated EEG waveform. That's your raw signal, the moment-to-moment voltage changes, the combined output.
The squiggly line?
The squiggly lines, exactly. But then you have the power spectrum. This one's key. It's the result of a calculation, a fast Fourier transform, or FFT.
Right, the frequency domain.
Precisely. Instead of voltage over time, it shows you how much power or energy there is at each different frequency. It's like a spectral fingerprint of what's happening neurally.
Okay, now here's something I noticed looking at that power spectrum. You see the main blue line, the signal spectrum, but then there are these dotted lines too, the ideal overlays. And they don't quite match up, do they? Even if you try to isolate just one wave type, what's going on there?
Yeah, that's a great observation. It actually points to something really fundamental about how signals combine. It's a fantastic way to visualize it.
Okay.
So think of the blue signal spectrum as the final dish, the total mix of all your ingredients, delta, theta, alpha, beta, plus any artifacts you threw in.
The whole cocktail.
Exactly, the
Yeah.
cocktail. The dotted ideal overlays, those show what each pure ingredient would look like completely on its own, in isolation.
Oh, okay.
But the final signal, the blue line, isn't just a simple sum. It's more like, well, like instruments in an orchestra. They interfere with each other. Sometimes they add up constructively. Sometimes they cancel each other out destructively.
Signal interference.
Right. This dynamic interaction happens across all the frequencies simultaneously. That's why the final mixed signal looks more complex, maybe a bit lumpy, compared to the smooth ideal curves.
So the overlays are like a guide to see what's supposed to be contributing.
Exactly. They help you mentally pick apart that real-world complexity, showing how those pure components are still driving the shape of that combined dynamic final signal.
Okay, that makes sense. So from building signals and simulation, let's pivot. Let's talk about a really critical real-world use, spotting seizures.
Yes, absolutely. This takes us to the EEG Seizure Detection Project, which is also called Rhythm Scan, and its whole mission is using machine learning AI to detect seizures from actual EEG recordings.
And how does it work? What's the input?
The core data it uses are these things called spectrogram images. They're basically sophisticated pictures derived from the EEG signals.
Pictures of brain activity.
In a way, yeah. They visually represent the rhythmicity, the timing patterns in the brain activity over time. And this visual format makes it much easier, especially for AI, to distinguish between a seizure event and, normal brain activity.
So how does the AI learn to actually see these seizure patterns in the spectrograms?
Rhythm Scan uses what are called convolutional neural networks, or CNNs.
Okay, I've heard of those, like image recognition AI.
Exactly like that. Think of it as a digital eye. CNNs are really good at extracting features from images, layers of complexity.
Wow.
So they learn to pick out the visual textures and rhythms in the spectrograms that are characteristic of seizures.
And how do you know if it's actually working well?
Right. Performance metrics are key. You look at things like accuracy and loss plots. These graphs show you how the model improves over its training time, accuracy going up, error or loss going down.
Makes sense.
Then there's the confusion matrix. This is really important. It breaks down the predictions.
Tell me more about that.
Okay, so it shows you 4 things. True positives, that's when it correctly spots a seizure. True negatives, correctly identifying normal activity. Then the errors. False positives calling something a seizure when it isn't.
Like a false alarm.
Exactly. And false negatives, this is the critical one where it misses an actual seizure.
Yeah.
In any clinical setting, minimizing those false negatives is absolutely paramount. You really don't want to miss a seizure.
No, definitely not.
Now, this brings up something really important, maybe a bit counterintuitive, about AI. If you take the same model, same settings, and train it twice, do you get the exact same result?
I'd assume so, if the settings are identical.
Often no. And the source material actually gives a great example of this.
All right.
It compares 2 training runs, run 9 and run 10. Identical settings, same batch size, 64, same number of training cycles, 100 epochs, same learning rate, 0.0001, no data augmentation, data shuffling was on, everything the same.
Okay.
Yet, run 9 achieved a test accuracy of 96.67%, while run 10 only got 90.00%. And their final losses were different too.
Wow, okay. So identical setup, different results. Why does that happen?
Yeah.
And given that variability, how much can clinicians, really trust these things for something as serious as seizure diagnosis?
That's the million-dollar question, isn't it? The variability comes down to what we call stochastic factors, basically. Elements of randomness in the machine learning process.
Like what?
Even with the same settings, things like how the network's internal weights are randomly initialized right at the start, or the slightly different random order the data batches get presented in during training. These small random variations can nudge the model down slightly different learning paths.
So it's not deterministic.
Exactly. It highlights the probabilistic nature of ML. And for critical uses like medicine, yeah, it means we can't just run it once and say, job done. It forces us towards much more rigorous testing. Running multiple experiments is key, averaging results, using techniques like cross-validation to make sure the model is genuinely robust and not just lucky on one particular run. Careful tuning of those hyperparameters becomes even more vital. It's about building confidence through repeated, consistent performance.
So thinking about the future then, what are the big hurdles still to overcome, and where is this AI-driven diagnosis heading?
Well, we're definitely making huge progress, but yeah, challenges remain. Fine-tuning those hyperparameters optimally is still partly an art.
Hmm.
And dealing with data imbalance is a big one. In reality, you have way more normal EEG data than seizure data. Making sure the AI doesn't just get lazy and predict normal all the time is crucial.
Okay.
Looking ahead, the goals are really exciting, making the models even more robust, maybe using more advanced architectures like resonance or LSTMs. But a huge focus now is on interpretability.
Explainability, right. Why did the AI make that call?
Precisely. For a doctor to trust an AI diagnosis, they need to understand the reasoning behind it, not just get a yes-no answer. That trust is essential. And of course, the ultimate goal is real-time processing. Imagine systems that can monitor patients continuously and flag potential seizures instantly for intervention. That would be game-changing.
Absolutely.
And you know, seizure detection is just one piece. There are other cool tools emerging for analyzing complex biomedical signals.
Like what else?
Well, there's something called joint time frequency scattering for seizure detection. It's a bit of a mouthful.
Sounds complex.
It is, but the idea is powerful. It goes beyond standard methods to look at signals across multiple scales simultaneously. This helps it capture really complex seizure patterns, ones that are stationary, that change over time. It can reveal subtle features other methods might miss.
How does it do that?
It decomposes the signal in a clever way. And users can actually play with parameters, like a scale parameter, to smooth the analysis differently, or change the EEG data length to look for patterns over longer or shorter times. It helps you hunt for those recurring, subtle signatures.
So if this scattering technique is designed for those really tricky, non-stationary seizure events, what kind of things might it uncover? What hidden features that maybe older methods just smoothed over or missed entirely?
That's exactly the kind of question it helps answer. It might reveal, say, very brief, high-frequency oscillations nested within a slower wave pattern, something a standard spectrogram might average out. Or it could highlight how the relationship between different frequency bands changes dynamically right at the start of a seizure, features traditional FFT might obscure. It's about capturing those transient, multi-scale interactions.
Fascinating. And speaking of seeing things differently, that brings us to another tool you mentioned. Seizure Zone, interactive 3D brain mapping visualizer.
Yes, this one is less about analyzing signals and more about understanding the brain itself anatomically.
So its main goal is education, deepening understanding of neuroanatomy, especially how it relates to functions and symptoms like in epilepsy.
Exactly. It uses a really detailed 3D brain model based on a standard map, the Destry Atlas.
Okay.
And what you do is select semiology examples, basically, lists of symptoms someone might experience during a seizure.
Right, like seeing flashing lights or feeling tingling.
Precisely those kinds of things. And when you select a symptom or a group of them, the tool highlights the specific brain regions thought to be involved, and it gives you descriptions explaining the connection.
Now, I saw it uses AI, specifically OpenAI's GPT-4o model, to help generate those descriptions. That's obviously cutting edge for making it user-friendly, but how do you ensure the medical accuracy, especially with that big disclaimer saying it's just for education?
Yeah, that's a super important point. The AI, GPT-4o in this case, is primarily used to translate the complex neuroscientific information into clearer, more accessible language.
So it's more about communication style.
Largely, yes. The core anatomical mapping and the symptom-to-region correlations themselves are based on established neurological literature and databases curated by experts. The AI helps phrase it understandably. But that disclaimer is absolutely crucial.
Cannot stress that enough.
Absolutely. It must be crystal clear. Seizure Zone is for learning, for exploration, for information only. It is not a diagnostic tool, not a substitute for seeing a qualified medical professional. No way.
Got it.
And really, Seizure Zone, the EEG simulator, the rhythm scan detection project, they all fit under this umbrella called the BioniChaos project.
Ah, okay. What's the goal of BioniChaos?
It's this really interesting initiative trying to blend biology, technology, and even art. The aim is to create these kinds of innovative educational tools to make neuroscience less intimidating, more accessible, to sort of demystify the brain.
And it looks like BioniChaos covers more ground, too. I saw mentions of things like AI decoding speech from EEG signals.
Yes, that's another fascinating area.
And brain-computer interfaces, like the Stentrode.
Exploring how we can connect minds and machines.
Plus, looking at the ethical side of things, like neural implants, and even commemorating 100 years of EEG research. It seems like a real hub.
It really is. It's trying to capture that whole exciting intersection of brain science and technology, from fundamental understanding to cutting-edge applications and the societal questions they raise.
Wow. What a journey we've taken then. From simulating brain waves, uh, teaching AI to spot seizures, to exploring the brain in 3D.
Yeah, quite a tour.
It really feels like these kinds of tools are, I don't know, opening up complex science, making these deep insights way more accessible than they used to be.
I completely agree. And if you sort of zoom out, connect this to the bigger picture, these interactive tools, often powered by AI, they aren't just pushing research forward. They're fundamentally changing how we learn about the brain, how we interact with this incredibly complex organ. So the question to maybe leave you with is, what's next? What new discoveries will these increasingly powerful, increasingly intuitive interfaces unlock? And maybe even, how could you get involved, engage with this field as it keeps evolving? What part might you play?
Okay, there's a human in the loop, just in case you're wondering. I didn't want to load this one because loading it actually, I might actually start dropping frames from the video recording. I mean, we're meant to be testing these things. Am I gonna? No, it didn't drop a single frame. That's quite impressive. I think my machine is in performance mode. Put it into balance mode so the noise from the fans and everything is not that loud. Anyway, that's what it looks like, if you're wondering. Yeah, the robot Notebook LM was actually talking about this one. So yeah, what did we cover? Yeah, I'll pop. Yeah, we covered this 4 tools. Yeah, this interactive 3D brain mapping for epilepsy, the joint time frequency scattering. Yeah, you can test it out. I popped all the links into the chat. Yeah, we have this model training on the spectrum, EEG spectrograms, with seizure and without seizure. So it's able to essentially make a diagnosis. And I believe it will be better than what a trained clinician can do. Well, purely because it has like infinite time and it's already overperforming. So if your data is in this specific format, well, this one is 600 images, this data set. But even a couple hundred of images, it would not make it possible. That amount would not make it possible for a clinician to just review in one sitting, whereas this thing does it in seconds. Reviews all the 600 images, trains on them. You can give it another image, it will just spit out the result. Is it a seizure or not seizure? And currently it has an accuracy of like 98%. Sometimes it goes even up to 100. 96, 98. Yeah, and this one 100. So it's a convolutional neural network with 100 epochs, 64 batch size, initial learning, augmentation, turn to false, shuffling is true, optimizer, and random seed as like standard in the field. So you can give it another image to this model and it will spit out a result. What else we've got? Yeah, we got that advanced EEG signal generator. Obviously, you must have already checked it out. Yeah, so everything we do is on BioniChaos.com. Go check it out. Let us know what you think. You can select your categories. We're currently looking at neurological, so EEG and neuro stuff. We have another overview on hearing. And again, there's a human in the loop. If you have any questions, go for it. Sometimes they don't fit into the screen well. You have to adjust your screen size or get a bit bigger, better screen. But no, this video is not sponsored by screen manufacturers. Luckily.
Welcome to the Deep Dive, where we plunge into fascinating topics and extract the most surprising insights just for you. Okay, close your eyes for a second. Imagine the richness of a full symphony orchestra, right? Every instrument crystal clear. Now flip that. Think about trying to chat with a friend in a really loud, bustling cafe.
Yeah, tough.
Exactly. Sound is incredibly complex, and for millions, hearing isn't straightforward. It's this frontier of constant innovation, really. And we've come such an incredibly long way from the early days of hearing devices. They were so clunky.
Oh, absolutely. It's almost hard to picture now. I mean, can you imagine those very early cochlear implants? Users literally had to carry around a large box of electronics just to make them work.
A whole box. It's wild.
It really is an almost unimaginable transformation from that, the literal box to the sophisticated, sometimes nearly invisible tools we have today. It's just decades of relentless science and, frankly, amazing ingenuity.
It truly is, and that's really our mission today. This deep dive is all about uncovering the cutting-edge science, the surprising breakthroughs, but also the tricky challenges behind making these devices really work, really transform lives.
Right.
Our goal is to give you a shortcut, basically, a way to get well-informed about all the hidden complexities, the advancements in hearing tech, from those pioneers back in 1975 right up to what's happening in the labs today. So let's unpack this journey.
Okay, so the story really picks up steam around 1975. That year, you had two separate teams working completely independently who made huge strides.
Right.
One was led by Professor Graham Clark down in Australia. The other was Drs. Ingeborg and Erwin Hochmer in Austria. They each pioneered the first multi-channel cochlear implants, building on some important earlier work that dated back even to the 50s.
And wow, did that work pay off. These devices, they got FDA approval in 1985.
Yeah.
And fast forward to now, estimates are over 1 million people worldwide have benefited from a cochlear implant. That's a massive impact.
It really is.
Yeah.
And the technology itself has just leaped forward since then.
Yeah.
I mean, forget just shrinking down from that large box.
Right.
We've seen incredible improvements. Modern implants or electrodes, way better speech coding strategies, much more comfortable to wear.
Okay.
People can wear them comfortably for ages. They're MRI compatible now, which is a big deal. There are even off-the-ear processors, for sports and active lifestyles.
And it's fascinating, too, how those initial breakthroughs didn't just help people hear, they basically spawned whole industries.
Exactly.
Professor Clark's work led to Cochlear Ltd. In Sydney. The Hochmers founded Med-El in Austria. And they're still huge players, right? Along with advanced bionics. It's this whole global ecosystem focused on pushing the tech forward.
Absolutely. And what's really striking is that these implants are now the gold standard treatment for severe to profound hearing loss. But things keep improving the tech, the surgery, so they're actually being considered for a wider range of conditions now.
Like what kind of conditions?
Well, people with moderately severe loss, sometimes, or those with severe loss in just one ear, that's single-sided deafness. And even folks with what they call steeply sloping hearing loss. The impact on quality of life for kids and adults, it's just immense.
And the innovation isn't just the outside stuff we see, right? The part that goes inside, the electrode array, that's seen big changes too.
Oh, definitely. They're thinner now, which can mean, shorter surgery, less discomfort. They're tougher too, more robust for just everyday living.
Okay.
But here's where it gets really like sci-fi.
Right.
Current research is looking into designing these electrodes to slowly release drugs.
Wow, drugs directly into the cochlea.
Exactly. The idea is it could help stabilize cells that might be affected by the surgery itself, or maybe underlying conditions. It's this amazing potential blend of tech and biology.
That is next level.
And this ties into a bigger question for researchers.
Yeah.
How do we make the experience of hearing better? Not just louder, but, richer.
Right, the quality.
Exactly. So modern CI sound processors have really cutting-edge tech inside. They analyze the sounds around you and automatically tweak the settings for the best hearing. And advances in the algorithms, the software, have made a huge difference in how well users can perceive non-speech sounds. Music, for instance, is much clearer, for many people now.
That's huge. Music is so important.
It is. And there are even special programs designed for tonal languages like Chinese, where tiny pitch changes are absolutely critical for meaning.
That makes sense. And thinking about usability, the Bluetooth integration must have been a game changer.
Oh, massive.
Yeah.
A major leap. Being able to connect directly to your phone, stream audio, even get remote support from your audiologist without leaving home.
Yeah.
It's turning it from just a hearing device into more of a connected health solution, really.
So much R&D money going into this.
Millions every year.
Yeah.
Making them smaller, faster, better connected. And beyond the hardware, there's a lot of work on predicting outcomes better, making sure each person gets the absolute most benefit. And another interesting research path is looking at whether CIs, like hearing aids sometimes can, might help reduce tinnitus for users.
Okay, so that's the amazing world of cochlear implants. Let's switch gears a bit now and talk about hearing aids, because even though CIs are for more severe loss, there's a quiet revolution happening with regular hearing aids too, right? Especially in how they sort of sense the world.
Absolutely, particularly with acoustic simulation.
Acoustic simulation, tell me more.
Well, think about the directional microphones in modern hearing aids. Making those work optimally isn't just about the software inside. It really depends heavily on the acoustics right around the hearing aid itself.
Okay.
So the sound pressure hitting those little microphone inlets is affected by everything where the mic is on the hearing aid shell, the shape of the inlet port, and really critically, how the aid sits on the person's head.
Right, so many variables. How on earth do researchers deal with that complexity without just building like a million prototypes?
Yeah, good question. They use some incredibly advanced tools. One is the Kimar mannequin. That's a special mannequin head and torso built specifically for acoustic testing.
Ah, I think I've seen pictures of those.
Probably. And then they use sophisticated computer models called finite element models, or FE models.
Finite element, okay.
With these FE models, researchers can actually simulate the acoustic response of completely new hearing aid shapes that only exist as virtual designs, CAD figures on a computer.
So they can test it before they even make it?
Exactly. It lets them do full 3D spatial response analysis. That's way beyond the older, simpler 2D measurements. They can even factor in subtle things like head shadow.
Head shadow, you mean your head literally blocking sound?
Precisely. Your head can block sound coming from certain directions, and that affects how the hearing aid picks it up. These models can account for that.
So they can test countless virtual designs, see how sound waves bounce around, predict performance. That must save an enormous amount of time and money in development, right?
Exactly. It's a
Yeah.
huge advantage. And once you can virtually test how the sound interacts with the device, the next big question is, okay, how do we make it sound best for the person actually wearing it?
Ah, right. Which brings us to user preference.
Exactly. And how different processing features interact.
Okay, so let's get into that. These features like wide dynamic range compression, WDRC, and digital noise reduction, DNR, maybe frequency compression, FC. How do they play together? What do people actually prefer?
Well, what's kind of surprising from some recent research is how they interact in maybe unexpected ways.
Huh.
There was a study looking at different settings, mild versus strong, WDRC and DNR, FC, on or off, all within typical settings an audiologist might use.
Okay.
And when there was a fair bit of background noise, people actually preferred a combination of slower WDRC and milder DNR.
Slower compression, milder noise reduction. Okay. But hang on, there was a twist, wasn't there? Something counterintuitive.
Yes, this is the really interesting part. When they used a stronger digital noise reduction setting, users then actually preferred faster, more aggressive WDRC.
Faster? See, that feels backwards. Wouldn't faster compression mess with the sound more?
You'd think so, right?
Hmm.
But it seems to be about signal fidelity, basically, how true the output sound is to the original, without adding distortion or losing details. Faster WDRC can sometimes distort subtle timing cues in speech, making it sound a bit less natural.
Mm-hmm.
However, when you have strong DNR working hard, it's already cleaning up the noise before the compression stage. So it effectively kind of buffers or tempers the distortion that the faster WDRC might otherwise introduce.
Ah, okay. So the strong noise reduction makes the fast compression sound better, clearer.
Exactly. Makes it more tolerable, and in that context, actually preferred. The DNR cleans things up first.
And what about frequency compression, FC? Did that make a difference?
That was the other surprise, really. In these kinds of clinically realistic settings, turning FC on or off didn't significantly change user preference or measured signal fidelity. It wasn't a major factor for preference here.
Interesting. So it didn't really move the needle much.
Not in this context, no. And if you think about the bigger picture, it really highlights this delicate dance between the algorithms. WDRC, especially fast WDRC, can actually sometimes make the signal-to-noise ratio worse because it amplifies the low-level noise in the gaps between speech sounds.
Right. Brings up the quiet bits, noise included.
Exactly.
Ah.
But when you add DNR, it specifically targets and reduces that noise before the compression happens, so it counteracts that effect. That's likely why stronger DNR makes faster WDRC work better for the listener, better audibility, and better comfort.
It's all about that sophisticated balancing act, isn't it?
It really is.
Okay, fascinating stuff. Now let's talk about what feels like one of the most ambitious frontiers right now. Combining different types of technology, like a cochlear implant in one ear and a traditional hearing aid in the other. That's bimodal stimulation, right?
That's right, bimodal. Or sometimes using both a CI and a hearing aid in the same ear. That's called electric acoustic stimulation, or EAS, sometimes called a hybrid system.
Hybrid, okay. And what's the potential benefit there? Why combine them?
Well, the potential benefits are actually pretty significant. We're seeing improvements in understanding speech, especially in noisy places, better overall sound quality, people often report. Music perception can be enhanced.
Music again, yeah?
And even figuring out where sounds are coming from, sound localization, can get better. And interestingly, even people with just a tiny bit of useful low-frequency hearing left, just enough maybe to hear the lowest parts of speech, even they can get substantial benefits for understanding speech overall with these combined systems.
But I'm guessing it's not just a simple plug-and-play situation. You mentioned earlier that current devices weren't always designed from the ground up to work together perfectly. So what are the sticking points, the complexities?
Yeah, it's definitely not plug and play yet. There are several key challenges. A big one is something called place mismatch in the cochlea.
Place mismatch?
Yeah, I mean, the electrical stimulation from the CI might activate a different place on the hearing nerve than where that sound frequency would naturally stimulate it acoustically.
Ah, okay. So the signal's hitting the wrong key on the keyboard, so to speak.
Kind of, yeah. Now, the brain is amazingly adaptable. It has plasticity, and it can often learn to reinterpret these slightly mismatched signals over time. But
it takes time.
it can take months, sometimes even years. And that adaptation might not be perfectly complete for everyone. It's a real relearning process for the brain.
That makes total sense. The brain's doing some heavy lifting to rewire itself. Is there like a typical adjustment period?
It varies hugely between individuals, but yeah, it often involves a fair bit of focused rehabilitation over many months. And another major challenge is synchronizing the timing information between the two devices.
Timing.
Specifically, what we call temporal fine structure and envelope timing cues. These are super precise timing details in sound, down to tiny fractions of a second.
Okay.
Our brains use these incredibly fine cues to figure out pitch, and crucially, exactly where a sound is coming from. But some current CI processing strategies tend to, well, they kind of smooth out or quantize these vital timing details.
Quantize, like making it blocky. So even if the basic rhythm is there, the super fine timing that helps you pinpoint a sound source gets kind of blurry, like a low-res sound picture.
That's a great analogy. Exactly. Some strategies round off timing information to levels that are just much coarser than what our brains naturally use for precise localization. So you get these temporal synchronization problems. The delays between the electric signal from the CI and the acoustic signal from the hearing aid can end up being much larger than the natural timing differences our ears rely on. And how loud the sound is in each ear, the interaural loudness difference. That's another tricky thing to balance perfectly in these combined systems.
And then there's the whole issue of just setting up the CI itself, right? How do you decide which frequencies go to which electrodes when you also have acoustic sound coming in?
Right. That frequency to electrode mapping. Studies looking for the best map, maybe a standard one, or one that deliberately leaves a gap between the electric and acoustic ranges, they've actually been pretty inconclusive. Different patients seem to prefer different approaches.
So it's very individual.
Very. And this brings up a really important point for long-term use. What if the person's remaining natural hearing changes over time, which it often does?
Ah, good point.
If you drastically change the CI map now to fit their current hearing, maybe disable some electrodes, only map high frequencies, and then their low-frequency hearing gets worse later.
Then the map is wrong again.
Exactly. It could mean needing another surgery to revise the implant, or even a whole reimplantation, leading to brand new, potentially lengthy adaptation periods all over again.
Wow. Okay. That's Yeah, that's a lot to juggle. It really underscores how incredibly personalized and dynamic this technology needs to be for each person across their lifetime.
Absolutely. And what's exciting, actually, is the intense research happening right now into unified sound processing platforms, systems designed specifically for bimodal or EAS from the start.
Okay, so trying to build that synergy in from the beginning?
Precisely. The goal is to manage loudness better across both ears, improve the accuracy of those crucial timing cues in the electric signal so they match the acoustic ones perfectly, really aiming for truly optimal binaural hearing, letting both ears work together as seamlessly as possible.
So when we boil all this down, what does it really mean for us, for you listening? This deep dive, I think, it really shows this incredible, intricate dance, doesn't it, between our own hearing, the cutting edge tech, and this relentless scientific research.
Mm.
It gives you, hopefully, a much deeper appreciation for the sheer amount of science that goes into what might seem like, just simple hearing help.
It absolutely underscores that it's far, far from simple. Every little piece, from the tiny design of an electrode wire to the super complex signal processing to
Yeah.
getting the fit just right for one person, involves really intricate trade-offs and a massive amount of scientific work.
Yeah. And as we think about those millions of dollars being poured into R&D every year, making these devices smaller, quicker, better connected,
Hmm.
it makes you wonder, doesn't it? How might the next breakthroughs maybe in predicting outcomes better for individuals or using advanced AI, how might they totally reshape the experience of hearing?
Whoa.
We could be moving beyond just compensating for loss, maybe towards a new era of auditory potential. Imagine a future where your hearing device doesn't just help you hear conversations, but actively optimizes, maybe even enhances your whole sound world in ways we can barely even imagine today. What might that future sound like?
There is a human in the loop, and everything we do is available on BioniChaos.com. Go check it out. Let us know what you think. Oops, sorry. Got the feedback. Something wrong with my microphone. Anyway, we don't worry about it. We are generating another overview. So we have about
The screen displays a web page from BioniChaos focusing on hearing. There's an audio overview at the top, and below that, there are several interactive simulations, like an interactive spectrogram generator, a cochlear limited of visual analysis, a cochlear simulator, and an interactive cochlear implant insertion simulator. This page is the cochlear simulator. On the left, you see a spectrogram visualizing sound, and on the right, there's a spiral diagram representing the cochlea with electrodes along its structure. It allows you to adjust the array type, number of electrodes, color scheme, and noise gate, letting you simulate different cochlear implant configurations and how they affect sound perception. It's a useful tool for understanding the technology. Based on the spectrogram alone, it's challenging to determine the exact words you are saying. Spectrograms represent frequency distribution of sounds over time, which can show the phonetic structure of speech, but they don't provide the specific words themselves. It would be difficult to accurately transcribe your speech without additional information or context. Yes, the simulation also features a spiral diagram that visually represents the cochlea and the placement of electrodes within it. You can adjust the number of electrodes and the way they are arranged, which helps understand how different configurations might impact hearing perception by stimulating different parts of the cochlea. It's a clear visual representation of how cochlear implants work. The spiral representation mimics the natural shape of the cochlea, where different frequencies are processed at different points along its curve. The linear representation, on the other hand, shows the electrodes in a straight line, simplifying the visualization of their placement along the frequency range. Both represent the array of electrodes, but the spiral provides a more anatomically accurate view of how they interact with the cochlea. Certainly. Besides the array type, you can also adjust the number of electrodes using a slider, which changes the resolution of the simulation. The color scheme lets you change the visual representation of the frequencies. Additionally, there's a noise gate control that you can enable and adjust the threshold for, which helps filter out background noise and focus on the relevant sounds. Imagine the cochlear simulator as a way to see and understand how a cochlear implant works. The spectrogram on the left is like a picture of sound, showing the different pitches and how loud they are. The spiral on the right represents your inner ear, and the electrodes are like tiny messengers that carry sound signals to your brain. You can change how many of these messengers there are and how they are arranged to see how that affects how someone hears sound. The noise gate helps block out extra noise so you can focus on the important sounds. It's like a virtual lab to explore how cochlear implants work. For a first-year university student, this simulator is a powerful tool for understanding the principles of cochlear implant technology. You can explore the relationship between sound frequencies, their representation in the cochlea, and the electrical stimulation provided by the electrodes. By adjusting the parameters like the number of electrodes and their arrangement, you can simulate different encoding strategies and see how they affect the perception of sound. It's a hands-on way to understand the complexities of biomedical engineering and hearing technology. The number of electrodes is being adjusted on the slider. You can see the number of colored dots in the spiral increasing or decreasing as the slider is moved. This changes the resolution of the simulated sound processing by the cochlear implant. You can also change the color scheme for the spectrogram and cochlea diagram using the drop-down menu. Additionally, you can enable the noise gate and adjust its threshold to see how it filters out background noise, allowing you to experiment with improving sound clarity in different conditions. The noise gate function filters out sounds below a certain threshold, which can help reduce background noise and make the main sounds clearer. When you enable it, the simulator will suppress the quieter sounds, ideally making it easier to hear the more important frequencies. If you don't see a significant difference, it might be because the current sound being simulated doesn't have much background noise, or the threshold is set too low to make a noticeable change. One interesting feature is the ability to see how different sounds are represented in the spectrogram and how they correspond to the electrode stimulation in the cochlea. You can experiment with various sounds and see how the unique patterns they create, which can be quite insightful and even amusing as you explore the relationship between auditory signals and their visual representation. It makes the abstract concept of hearing technology more tangible and interactive. The cochlear implant is a fascinating tool for studying the brain because it directly interacts with the hearing pathway. It essentially bypasses the damaged parts of the ear and sends electrical signals directly to the cochlea, which then stimulates the auditory nerve and sends signals to the brain. This allows researchers to study how the brain processes sound, how it adapts to receiving signals from an artificial source, and how it relearns to interpret these signals, offering unique insights into the brain's plasticity and auditory processing.
Ever wondered what happens when you bring together two really advanced hearing technologies? Not for two different people, but, perfectly tailored for just one individual. What kind of unique sonic world could that unlock?
Yeah, that's a great question.
Today, we're taking a deep dive into exactly that. The fascinating realm of bimodal hearing.
Right.
This is where a cochlear implant, or CI, in one ear works in harmony with a traditional hearing aid, an AHA, in the other.
A real team effort for the ears.
Exactly. We've poured over a stack of sources for this deep dive. I mean, everything from professional insights and blogs to detailed research papers and some pretty comprehensive systematic reviews.
A lot of material.
Yeah. Our goal is to really cut through the complexity and give you the essential insights.
And our mission for you, the listener, is to truly unpack the significant benefits of bimodal hearing, delve into the intricate challenges it presents, and discover how cutting-edge tech and tailored rehabilitation are not just supporting, but actually revolutionizing this field.
Helping people fully experience the joy of sound again.
Precisely. Helping people experience the profound joy of sound.
Okay, let's unpack this then. So, at its core, what is bimodal hearing, really? And why are more and more people, opting for this dual device approach?
Well, the fundamental goal really is to seamlessly integrate information coming from both ears.
Okay.
Think about it this way. A cochlear implant, it directly stimulates the auditory nerve, right? It essentially bypasses damaged parts of the inner ear.
Right, the electrical stimulation.
Yeah. Whereas a traditional hearing aid amplifies sounds using whatever functional residual hearing you might still have.
So leveraging what's still working naturally.
Exactly. And what's truly fascinating is that in quiet environments, there often isn't a massive difference between using just a CI alone and this bimodal stimulation.
Oh, really? Okay.
But, and this is the key part, the real game changer comes when we look at more challenging environments, like noisy places.
Yeah, the classic difficult.
Right. In those noisy situations, bimodal users show a significantly increased ability to pick out and understand speech. Much better than with just one device.
Wow. How does that work?
This crucial advantage comes down to something called binaural hearing, which is basically our brain's amazing ability to use both ears together to process sound.
Like stereo sound, kind of.
Sort of, yeah.
Yeah.
Your auditory system compares these tiny timing and loudness differences of the sound reaching each ear.
Okay.
And this skill is absolutely critical for knowing where sounds are coming from. Is that car on your left or right?
Yeah, super important.
And, of course, for understanding conversations in say, a bustling room.
That makes a lot of sense. And I guess the benefits expand beyond just understanding speech, right?
Absolutely. Our sources highlight definite improvements in music perception, too.
Oh, interesting. How so?
For example, studies show that performance gets significantly better with increasing acoustic bandwidth from the hearing aid when it's combined with the CI. More information helps.
Right, more range.
Exactly. And what's even more surprising is how powerful those very low frequencies can be. Even just a bit of acoustic hearing in that low range can really help with timbre perception.
Timbre. That's like the quality of the sound.
Yeah, exactly. It's that unique quality that lets you tell the difference between, say, a piano and a guitar playing the same note,
Yeah.
or a child's voice versus an adult's.
Gotcha.
And one study among children even showed a 14 percentage point improvement in timbre perception.
14%. That's actually huge. That's a huge difference in how rich and clear the world must sound.
It really is. And the advantages, they extend even further. We're talking overall quality of life improvements and even potential long-term boosts in cognitive functions.
Like what?
Things like learning, memory, language, executive function, attention. It's quite broad.
Wow. So this raises a really important question then. How does combining these two really distinct, complex technologies actually achieve such broad and impactful results across so many areas of life?
That is the million-dollar question, isn't it? It comes down to how the brain adapts and how we support that process.
Right. So what does this all mean for someone, maybe just starting their bimodal hearing journey? How do professionals guide this complex process? And how does the tech itself adapt?
Well, first off, monitoring a patient's progress is absolutely paramount all the way through.
Constant checks.
Yes. It's crucial to regularly evaluate the performance of both ears, individually and together. You need insight into the patient's auditory skills with each device.
Makes sense.
And this goes hand in hand with ongoing counseling, managing expectations, making sure rehabilitation plans align with what the patient actually wants to achieve.
Their personal goals.
Exactly. And keeping thorough records of all discussions. We're even seeing innovation here. Dr. Deepthi Mahadevappa from MedL, she's a speech-language pathologist and rehabilitation manager.
Oh, yeah.
She's actively involved in developing digital rehabilitation tools and supporting professionals globally in this very specific area. So tools are evolving too.
That's great. And that rehabilitation training you mentioned must be absolutely crucial, right, for improving listening abilities.
Oh, definitely. It's not just about getting the devices fitted and switched on. It's a comprehensive process.
Right.
It includes specific training just for the cochlear implant ear, then training for using both devices together seamlessly.
Integrating them.
Yes, and really focusing on specific exercises like sound localization, figuring out where sounds come from, and speech and noise training, practicing in tough environments.
Yeah. I imagine patients who've used two hearing aids before might have a bit of a head start with the hearing aid side.
That's true. They'll know how to process sound from their hearing aid. But learning to hear effectively with their cochlear implant, that definitely comes with its own unique learning curve. It's a different way of hearing.
Right, a new skill to learn.
And the acoustic bandwidth in the hearing aid also plays a really significant role here.
Bandwidth. Remind me, that's the range of frequencies.
Yeah, exactly. Think of it as the range of sound frequencies the hearing aid can pick up and deliver. And studies consistently suggest that providing the broadest possible acoustic bandwidth gives the maximum bimodal benefit for speech understanding.
So wider is better.
Generally, yes. And this holds true even for very low frequencies, like below 125 hertz.
That low? Really?
Yeah, they might seem almost negligible, but they turn out to be incredibly important for things like understanding male voices in noisy backgrounds.
Huh. Interesting detail.
It reinforces the idea that more sound information, even the really subtle stuff, is generally better for the brain to work with.
Okay, but it gets complicated, right? When we look at how the hearing aid actually processes that sound, I read there are some real trade-offs involved in the settings.
Oh, absolutely. It's not straightforward. For instance, take wide dynamic range compression, or WDRC.
WDRC, that adjusts the loud and soft sounds.
Right. It essentially squashes the range between the softest and loudest sounds to fit the person's hearing range. Now, if you have fast-acting WDRC, it can sometimes lead to poorer speech intelligibility and maybe a less pleasant sound quality for some listeners.
Okay.
So, slow-acting WDRC is often preferred, but
There's always a but.
there's always a but. If strong digital noise reduction, or DNR, is being used at the same time, then fast WDRC can actually be preferred.
Why is that?
Possibly because that strong DNR cleans up some of the background noisiness that fast WDRC can sometimes introduce. It's a complex interaction.
I see. And speaking of digital noise reduction, the DNR. I understand that cranking it up can sometimes compromise a little bit of speech clarity.
It can, yeah, there's a potential trade-off there.
Yeah.
But the upside is it consistently improves overall listening comfort and significantly reduces listening effort.
And that's huge for daily life, right?
Yeah.
Just not feeling so drained after a conversation.
Exactly. It's a massive quality of life factor. Then there's another feature, frequency compression, or FC.
Okay, what's that one?
That's where the hearing aid shifts higher frequency sounds, which someone might not be able to hear, down into a lower, more audible frequency range.
Trying to make those sounds accessible again?
Precisely. But interestingly, a study that used what they call clinically realistic settings, so not extreme settings, with start frequencies above 4 kilohertz, they actually found no effect of FT on preference or signal fidelity.
Oh, so it didn't help or hurt in that case.
In that specific, more realistic setting, yes. Which kind of goes against what you might expect if you're using more aggressive, lower starting frequencies for the compression. It really highlights how nuanced this fine-tuning has to be.
Wow. So the key takeaway here is that optimizing a hearing aid for a bimodal user isn't just about turning up the volume.
Not at all.
It's this sophisticated balancing act. Professionals have to fine-tune all these advanced settings, WDRC, DNR, maybe FC, to prioritize clarity or comfort, or maybe reduce effort, depending on the individual listener's needs and experiences.
Exactly. It's highly personalized. But the real challenge, arguably, lies in integrating the signals from these two fundamentally different devices, the electrical CI signal and the acoustic HA signal.
Right. One's electric, one's acoustic amplification. How does the brain handle that?
Well, that's the tricky part. Current commercial CI sound processing strategies, you might hear names like CIS, ACE, FSP, FS4. They often have to discard some information. Specifically, what we call temporal fine structure.
Temporal fine structure sounds complex.
It is a bit. Think of sound having a very detailed fingerprint, especially in its timing. That's the temporal fine structure. It includes incredibly tiny timing differences between when a sound hits your left ear versus your right ear.
Ah, the binaural cues you mentioned earlier.
Exactly. Your brain uses those cues, those minute timing differences, to know exactly where a sound is coming from. But when a cochlear implant converts that smooth, continuous sound wave into discrete electrical pulses...
Timing quantization you mentioned.
Right. That process can sometimes lose some of those subtle timing details. It's almost like simplifying a complex musical score. You get the main notes, but maybe lose some nuance.
Okay, I follow.
And this makes it really challenging to effectively transmit those crucial binaural cues, like interaural temporal differences, the ITDs, the timing ones, and intraoral level differences, the ILDs, the loudness ones.
So the CI struggles to deliver that spatial information?
To some extent, yes. In fact, with current commercial devices, ITDs are probably not perceptible at all.
Wow.
And ILDs, the loudness cues, are only partially perceptible. However,
Another but.
a positive one this time, advanced algorithms, specifically something called ILD emphasis algorithms, have shown significant improvements in localization performance. They can reduce the absolute error in pinpointing sound by about 4 to 10 degrees.
That sounds like a noticeable improvement.
It is. It highlights a critical frontier. While our brains are naturally wired to use these tiny timing and loudness differences, getting a CI to effectively deliver those cues is a major engineering challenge. But these algorithms show we're making really impressive strides.
Yeah, it's truly remarkable how specific algorithms can make such a tangible difference. I also read about another one, adaptive dynamic range optimization, or ADRO.
Yes, ADRO, that's another amplification strategy, different from WDRC. And it has been shown to improve speech recognition, both in quiet and in noisy environments.
Any specific conditions where it works best?
Particularly when the speech or the noise is coming from either the front or from the side where the CI is located.
Interesting. Okay. But even with all this tech, progress isn't guaranteed, right?
No, absolutely not. It's really important to acknowledge that progress with a cochlear implant varies significantly from person to person. Hugely variable.
What sort of factors influence that?
Oh, several things, like how long the person has actually worn the CI, their specific hearing history before the implant, the degree of their hearing loss, and even how long they were deaf before they got the implantation. All these play a role.
And there's another critical nuance here, isn't there? I saw that speech outcomes with bimodal listening, they can actually show high variability across subjects.
That's right, high variability. And in fact, for some individuals, they might even experience worsened speech performance when they add the hearing aid.
Worse. How can that happen?
It often seems linked to how effectively their brain integrates the speech information coming from the electric stimulation, the CI, and the acoustic hearing, the HA.
So a mismatch, maybe?
It could be due to differing performance levels between the CI alone and the HA alone, or sometimes a very long duration of deafness before implantation can make that integration harder.
So given that variability, I mean, what does that tell us about the brain's incredible adaptability, or maybe its limitations in these scenarios?
That's a fantastic question, and it brings us to another really key point. Bimodal listening might actually require increased cognitive skills.
More brain power needed.
Potentially, yes, because of the inherent challenge of integrating these two very different types of signals, especially when you throw in background noise. Your brain is working really hard to fuse it all together into a coherent picture.
Okay. So a crucial question then becomes, how do we make sure people get the right support for this complex integration process? How do we help the brain make those connections?
That's where the rehabilitation and careful programming come in. But also thinking about who benefits most. One area where bimodal stimulation can be a particularly powerful solution is for individuals with asymmetric hearing loss or